Rest for a while, and then we continue again for another 30 minutes. Okay, so good afternoon, class. Can you hear my voice or not?
Can, Doctor, can. Good afternoon.
Oh, good afternoon. Sorry, good evening, Beckham.
Yes, good.
Hi. Thank you, Jin. So I've recorded it. Okay. So by right, we should finish our topic until now. Is the 23rd of December. 23rd of December should be here lah, nah. But right, we need to cover those this type of topics, and then should be today should can be finished lah. If not, the second we can finish it by today. Sorry, until here. But I think we can finish it about these three topics today. Because it is it talk about introduction and it's quite theoretical, a little bit broad. No need to memorize. Just try to look through it, and then won't. I think it won't come out in the final exam, huh? But calculation, yes. Calculation, yes. And after that, we will have another two sections, which is a transformer design and an induction machine design, where we will do these two topics in problem-based learning lah. And I think problem-based learning will be distributed by next week. Oh, okay. So let's see. We start from. So I think we need to start from magnetic fields in electrical machines. We cover the simple synchronous generator, then it will go to the rotor-type synchronous generator, schematic view of three-phase machine, and also AC and DC machines. So let's have a look on the slide. Have I shared this slide for you guys? Maybe yes, maybe no, I'm not sure. Well, okay, so let's have a look on the magnetic fields. Magnetic field in the electrical machine. Usually we start from a simple one first. So we will have a simple two pole. One pole here, another pole here. Then single phase synchronous generator. So we have a phase A. Something like this lah. So if you still remember from the beginning, I told you that this subject would be a little bit different. Is that we're dealing with a material. Okay, one is material, then one is a space, space or geometry. This a few things lah. So space means when we need to know how good the flux going from the rotor to the stator and then cross and then coming back to here. So we need to know how good are the magnetic flux in the air gap, how good the magnetic flux density in the air gap. The more the merrier. But too much, it becomes creating unwanted torque or unwanted power. So that's why in a spatial magnetic flux density, we also need to know. For example, the B versus the theta. Theta start from zero here, 0, 90. By default, this is a positive direction. Then 180, then 270, then 360. So 0, 180, 90 here, then 360. So maybe from this point, I need to take it. I need to pick it up first, yeah. Maybe from this point, okay. The point the B is this value. So at this point, when the rotor at this instance, okay, it is not rotating at this instance. So the magnetic field maybe is like this. Right. Maybe it's like this. Magnetic field maybe it's like this. And then when it come to 90 degree, it is this point. When it go to the 180, it becomes 0. When it go to the 275, become like this. When it go, sorry, this is 270. Then go back to the 0, then to 0 degree, it becomes this point. Sorry, it should be this point. When it comes to 0, it should be at this point. Because it should be same. And then keep giving the same rotating point. So this is how that we also can find what is the magnetic flux density in this point, like this. For example, in this area, okay, or in this area, or in this area. But the problem is we are not interested on that region. We call region. Space, this is geometry, it's related to geometry. We are not interested on that region. But we only interested in the middle of the air gap because we want to know how good the magnetic flux crossing from the rotor to the stator and then get back to the rotor so that it can cross with our winding. And then if let's say there's a crossing by using the Fleming left hand rules or Fleming right hand rules, it can be generator or motor mode. Huh? That's why we only plot the V, usually is R, radial magnetization pattern, in the middle of the air gap. We call middle of the air gap. So if let's say maybe we get one cycle is like this, okay, something like this, so we can see that the magnitude here, maybe this is 0.2 Tesla for motor 1. Then this is maybe 1.5 Tesla for motor 2. So when the B is higher, the EMF will be bigger, which means the voltage generated will be more compared to the voltage generated by this motor. So higher EMF, the better the motor line, right? So that's why we need to know the magnetic flux density in the middle of the air gap first before we go to evaluate the EMF. Then at the same time, we also can evaluate the B into EMF by using the Faraday's law. If let's say you still remember, E and F, V equals to negative N d phi dt. Phi is related to B. Okay, so this is how we want to know the basic from the magnetic flux density. Yeah, I forgot to introduce you this the diagram. Maybe the diagram. Okay, for example, we have armature winding, the winding that used to generate, capture the current, or we supply the current to let the motor run. Then another one we call field winding. Field winding is the winding for us to inject some current so that it can create the magnetic field to interact with the magnetic field that generated by the armature winding. As I told you before, in order to make a thrust, a movement of the motor, it must be one from the stator, one from the rotor. If let's say we only have a magnetic pole from the stator without rotor, then it becomes nothing. Or if let's say we only have a pole on the rotor without stator pole, then it becomes nothing. So in order to make a movement, either repulsion or attraction, we need to have a two magnet. Either one is static part, one is from static part, one is from the rotating part. So that's why we have a magnetic field from the armature winding, magnetic field from the field winding. So, and then, okay, this one is called a salient pole rotor. This type, this type of rotor we call salient pole. Why we call like this? Because actually we inject, uh, they have a a winding crossing through this pole, like this. A winding crossing through this pole. Okay, and then it create a stator pole in here. I mean, it create a stator a field like this. So they call salient pole. Just put it in a simple way. Salient pole means we need to coil something here. We need to coil something. So in here we have two things. One is a space distribution of flux density. This one is called space distribution of flux density. In the space, maybe I need to take off this one first. In this space, there's no touching of any material. I mean the magnetic material. For example, the stator core or rotor core or anything, none. We interested in the space distribution of flux density. And then from the space distribution flux density, we can further derive into the corresponding waveform of the generator voltage for the single phase generator. So this type, maybe it is used to design as a generator. And this all of this info are taken from the chapter 4 AE Fit. Please to write from the electric machinery McGraw-Hill publisher. If let's say you want to read further, then you can have a look on that. But anyway, it won't come up from the examiner. So then we extend to four pole, a simple four pole single phase synchronous generator. So also same single phase means we only have a phase A. Four pole is one pole, two pole, three pole, four pole. So one coil, two coil, three coil, four coil. All are field excitation. And then phase A, single phase, phase A, A1, A2. Even though there's a different numbering, it's still under single phase. So spatial distribution of the air gap flux density is idealized. Four-pole synchronous generator. So B versus the theta, maybe from here, 0 degree is this one. And then 2 pi is 330, right? It's also 0. So we can see 180 is here. Okay, is also 0, which means, let me pick up this one first. Which means, let's say this one is 0.1. So this is the point. So 180 is here. Then if let's say we take center, 90 is this one. And then if let's say we take 270, this is here. So this value B here, let's say B3 is at here. The value of B3 is at this instant. So I think this one we go through already. Whenever we want to convert the mechanical degree to electrical degree, always use mechanical degree times pole pair, P. Then also the same, let's say we want to convert uh, uh, frequency, we need to use this one. For example, F equals to NP over 120. In fact, the N is the revolution, P is the number of pole, 120 is a constant value, it's come from here. So frequency is the frequency of the electrical, which means this one is mechanical degree. What if when we want to convert the B to EMF? I believe that you are very good in EMF because when from the instrumentation, when we want to measure the voltage, what we do is voltage versus time. So there are different time scales. One is mechanical degree, one is a time. So how to convert into here? Yeah, this is one of it. Let's say the frequency here will be 2 cycle. This is called 1 cycle, right? Then when we draw in the EMF, it will be a little bit different. Maybe it is more cycling. Yeah. Maybe it will be more cycling. Yeah. So it's very important for this formula. So rototype of a synchronous generator, elementary two-pole silent rotofield winding. So two-pole, usually the most minimum is a two-pole. Out is a new, when the field is going out, we always consider as a north pole. When the field is going into the center, we call as a south pole. Two pole, one pole here, another pole here. We also have a cylindrical rotofield, also known as non-salient rotor. Just now we say that when talk about salient rotor, it's a winding like this, right? It is winding like this. But you will say, hey, Dr. Tiang, how come this one also winding? But you told me that this is non-salient rotor. Have a look differently. You see the, have a look carefully. For this salient rotor pole, it will directly create a, it will directly create a flux path in this way. Same as well, we also create a flux path in this way. We have a north pole, north pole. We have a south pole, south pole. But we wind according like this, which means we wind like this, we wind like this, we wind like this, so that when we excite, you see all the current go in. This is current go out, go out like this. Current go out. In this part, all the current going out in this part, all the current going in. By using the right hand rules, okay, by using the right hand rules, the field will created to the top as a north pole, and the bottom will be the south pole. Eventually, the flux path are the same as here. Okay, the flux path are the same as this one, just that the we call motor construction are different. Huh? So just for your information, this one we call salient rotor pole, this one we call non-salient rotor. Okay, schematic view of a three-phase generators. Just now we only have a one phase. Now we have a three-phase, which means we have a phase A, phase B, phase C. By right, I need to teach you this one first before we go into the winding layout. But I think I already integrated it to become easier way. It is easier to understand from three-phase to single phase instead of from single phase to three phase. For this kind of topics. Then we have a two pole, we have a four pole, we have a Y connected winding. So let's have a look. Where is a three phase? A, A, B, B, C, C. This one is called armature winding. Armature winding is the winding that can give us the useful current if let's say we want to use it to for power up something. For example, this current is not useful to us. This one is only used for create an excitation field, create another pole of excitation field. We are not using the main bus power from TMB to inject this one, no. But armature, yes. Armature is the one that used to withdraw the current from the motor or supply current to the motor to run it. Right? So this one is three phase, two pole. What about here? Phase, there's A, then A, there's A again, A. Okay, so and then we have a four pole, 1, 2, 3, 4. And then remember, when we place the pole, it must be alternative. For example, when this is start from north, the side must be south, then going back to the north, and then going back to the south. We cannot simply put like this. We cannot simply put, this is north, north, south, south. No, this is wrong. Okay, so in three-phase system, for the Y-connected winding, uh, no matter phase A, phase B, phase C, it only one wire in and one wire out. And all the wires are connected in series. For example, let's say we call this as A1. Then this is our negative A1, A1 plus, okay, A1 minus. Then this is our A2 minus, this is our A2 plus, for example. So if let's say we draw like this, okay, so in, out for phase A. So usually we will go to plus first. So this one is A1 plus. Then we go to A1 minus. Then from A1 minus we go to A2 plus. We connect to A2 plus. So this one will be A2 plus and then go up to A2 minus. So it must only have one in and one out for one phase. So for example, we directly put like this, one in, one out. So A minus. So A minus. A prime, negative A prime. A prime, negative A prime. Same goes to phase B and phase C. So notice that the angle displacement between the phase winding is 120 electrical degree. So from here we cannot see it is 120 electrical degree lah. But for the rule of thumbs, we need to design phase A, phase B, and phase C with 120 electrical degree so that it can have a balanced phase. Elementary DC machine with a commutator. If you still remember the video that I shared to you during the first class or second classes of our lecture classes, we talk about the DC machine with the commutator. So this is the commutator lah, nah. This part is commutator. Then we have a carbon brush. Then we have armature coil. Then we have excitation. This is north. This is south. So we can see that okay. Uh, the armature is at the stator part in this machine. However, in the DC machine, the armature is inside. So that's a little bit different, but the functioning are still the same. For armature, it's only useful when we want to draw it or we want to supply it instead of the excitation field. Excitation field is for us to create another pole to interact with the armature pole. So same as well, we also need to analyze the spatial distribution magnetic flux density. Spatial, space, which is middle of the air gap. So where is the middle of the air gap? This line is the middle of the air gap. We want to know how good is the B in the middle of the air gap. So for example, this is a 2 pi. Usually we start from 0 here. And we know that this is North Pole, this is South Pole, then the North will be crossed like this. So which means the fluxes crossing here will be less. Okay, usually it's almost 0. So we can see that at the 0 position, it is 0. At a set 90-degree position, it is maximum. 180, 0. 270, maximum in a negative position. Why is a negative? Because in the south direction, which means it's going out from the center. For example, the North Pole now is going in, right? So it will positive like this. Then when the field is going out from the center, this is center, then it becomes negative plane. And then going back to the 0 again, and then repeat. So we can suspect, we also can use a common sense, feel that, okay, the flux here should be a little bit higher if compared and constant as compared to other places, for example, this one and this one. So become this one and this one. Or in a negative direction, that is. Agak-agak lah, huh? That is just assumption. And then when we change into from B to EMF, you see the theta to T, then it becomes the curve like this. So this is our EMF. So spatial distribution of air gap flux density in an elementary DC machine. Why it calls an elementary? Elementary means it is a concept whereby it is not the full construction of the motor. It is a concept. We put it in the most simple way. And then waveform of the voltage between the brush. So how to get this one? Same. EMF equals to negative N d phi dt, where phi is related to the B. Something like this. Or for example, phi equals to VA, right? Something like this. So from those few previous slides, what we want to convey the message to you guys is actually it is very important that we need to analyze what is the magnetic flux density in middle of the air gap, especially for this instance. So you will ask, hey, Dr. Tian, why not we consider the magnetic flux density in here? Can, but for what? It's not important and wasting our time, right? So don't go for that. Then MMF of the distributed winding. MMF, I told you before, MMF is let's say magnetomotive force as we have discussed in the winding layout. So first of all, before we want to decide where is the go direction, where is the return direction of the winding, someone, who is the May Salim? Okay, during the winding layout selection, we need to assume where is the MMF direction first. After that, we need to select the appropriate one so that we can have the best, I won't say the best, the highest efficiency of the EMF generated and so-called after efficiency due to the EMF, yes. MMF is something like the force generated due to the uh, magnetic field. That one is called MMF lah, huh? And then what we have, a schematic view of the flux produced by a concentrated full pitch winding in a machine with a uniform air gap. The air gap MMF is produced by current in this winding. So what else? For the Fourier series, I think this is out of your topic lah, huh? If let's say we want to convert to the Fourier series, that would be a little bit uh, out of your topic. But I need to brief you about this. So first of all, we need to know that the most important region that we are interested is the magnetic flux density in the middle of the air gap, which means this one, this one. So when we know where is the region, we need to plot it into a curve, in a graph. So from a zero position, this is the zero position. Take out this one first. Zero position, and then it would be the most maximum of the MMF, because when we use the right hand rules, and then we inject the current, right? This one is go in, this one is go out. Okay, then when we inject the current go in and go out by using right hand rules, we will see that our thumbs is going to this way. Our thumb will pointed to this way. When it's pointed to this way, which means this is the highest value of the forces. So we will put it as this one. Same as well, because we want to, we assume it is a uniform again. So all the forces will be towards like this. Same. Let's say this one is a 10 ampere turns. Wait, 10 ampere turns. Force MMF is a Weber. Yeah, F equals to Ni, whereby it is current ampere turns. Yeah, ampere turns. So let's say this is 10 ampere turns. So this line will be our 10 ampere turns. So from zero position, it is 10 ampere. At this position, it also 10 ampere. Sorry, this one is go forward. Alright. If let's say I go behind, then it's this point. And then this is towards this direction. If let's say we assume the direction is going out from the center is positive, then this will be the region. Then at the same time, when it's towards the center, it becomes negative direction. So this is the curve of the MMF. I mean the graph of the MMF. Okay. So next, oh yeah, I forgot to mention why we interested to do this. Actually, we want to know uh, how good the fundamental that we have here, this value. Actually, we can convert this square wave into a mathematics, and the mathematics is called Fourier series. A lot of components there, but in fact, we are more interested on fundamental one. The higher the fundamental, the better, because the EMF generated will be larger. So going back to the AC machine, the MMF of one phase of a distributed. Distributed means it's overlapping. We are not coil like this. Instead, we coil like this, something like this. So we call it overlapping. And then the characteristic is let's say this coil and this coil. So it will create yeah, this one is not. Maybe it will create this value. Then this coil and this coil, it will create this value. Then this coil and this coil, it will create another value. Something like this, this coil and this coil, it will create another value. So when we add up together, it becomes a sine curve. This is a distributed one. And then, okay, no need to care about the equation here. This is just for your information. Finish already. So this chapter is talk about magnetic field in electrical machines. And as a conclusion, I would say that the most important thing is we are interested in the middle of the air gap of the machine. So usually when we want to create the motor, we are trying to make the rotor and stator as close as they can. For example, induction machine, the air gap between them is about 0.2 mm. Induction machine, this air gap, you can use your ruler, have a look. How small is it? 0.2 mm. And then for permanent magnet, we usually put 1 mm. 1 mm. Okay? So, and then we will focus on the middle of the air gap here, magnetic flux density, so that we can know that how good the EMF can be generated. Okay, so I think that's all for this subtopics. Right? I think theoretically we are doing like this, but when we try to put it into winding layout selection, there will be another story. That's why I come out easy calculation of the as we discussed 2 weeks ago, how we want to calculate and determine the winding allocation by using all the calculation. If you still remember that we use a radar, right? That is the one we did it. I believe that you will come across to this situation when you do your mini project. Right? So any question from the floor? Any question? So okay, I think I will go to the induced EMF and talk. Oh, this one a bit a lot of equation, which is not very important. Huh? I think this is the induced EMF, inductances, and torque. Any question, class? Any question? Okay, if no question, I will proceed with the magnetic, the induced EMF, inductances, and torque. Okay, not for now. Okay, thank you, Jin. So next will be go to the induced EMF, inductances, and the torque. So in this topic, most important is the induced EMF lah. And then from the chapter 2, one of the equation generally we use is Faraday's law. EMF equals to V equals to negative N d phi dt lah, where we want to convert the magnetic flux density B into the EMF, which is induced. Why we call induced? Because the voltage generated without touching. There is no touching between the rotor and the stator. In fact, okay, I think we rest for the 10 minutes. After that, we come back again, yeah? Let me stop presentation, then stop recording first.